Have you ever wondered how crucial radiographic testing is in the realm of non-destructive testing? This ingenious technology enables us to examine the inner workings of materials and components without causing any harm. Imagine being able to look inside a jet engine or a gas pipeline without having to dismantle it. That's the magic of radiographic testing. Now, let's take a moment to appreciate its significance across industries. In the oil and gas sector, it's instrumental in ensuring the integrity of pipelines and storage tanks. In the aerospace industry, it aids in the inspection of aircraft parts, guaranteeing safety in the skies. Meanwhile, in the automotive world, it's indispensable for checking the quality of welds, thus ensuring the reliability of our vehicles. Radiographic testing is not just about looking inside objects, it's about ensuring safety, reliability, and efficiency. It's a silent guardian, a watchful protector of our modern world. Now that we understand the significance of radiographic testing, let's delve into the methods involved. Radiographic testing might seem complex, but it can be broken down into simple, understandable steps. Let's dive into this fascinating process together. Everything kicks off with the production of X-rays or gamma rays. This is achieved by bombarding a target material with high-energy electrons in an X-ray tube, or by the natural radioactive decay of isotopes, such as iridium-192 or cobalt-60. These rays are then directed towards the test object. Next, the X-rays or gamma rays interact with the test object. Just like how light can't pass through a solid wall, these rays can't pass through dense materials, so they get absorbed or scattered. But unlike light, these rays have enough energy to penetrate most materials to some degree. The amount of penetration depends on the material's density and thickness, as well as the energy of the rays. As these rays pass through the test object, any internal flaws or defects, such as cracks, voids, or inclusions, can cause variations in the intensity of the rays that reach the other side. These variations are due to differences in how much radiation gets absorbed or scattered by the defect compared to the surrounding material. Finally, the remaining radiation reaching the other side is detected. This is typically done using a photographic film or digital detector that's sensitive to X-rays or gamma rays. When the film or detector is exposed to the radiation, it produces a radiographic image similar to a medical X-ray. Areas of the image that received more radiation appear darker, while areas that received less radiation appear lighter. By analyzing these variations in darkness, skilled technicians can identify and evaluate any internal defects in the test object. Each step plays a critical role in revealing the unseen, ensuring the integrity of materials and components. While radiographic testing might seem like a complex dance of invisible rays, at its heart, it's a simple, elegant method to inspect the internal structure of materials and components without causing any damage or destruction. Radiographic testing isn't a one-size-fits-all approach. There are different methods tailored to specific needs. Let's delve into the world of radiographic testing and explore some of these methods. First, we have X-ray radiography. This method is like a super-powered version of the X-rays you might get at a doctor's office. It uses electromagnetic radiation in the form of X-rays to create an image of an object's internal structure. It's a versatile method, useful for detecting cracks, voids, and other internal defects in a wide range of materials, from metals to ceramics. Its main advantage is its ability to provide extremely detailed images. However, it requires electricity and heavy machinery, which can make it less suitable for fieldwork. Then we have gamma radiography. This method also creates an image of an object's internal structure, but instead of X-rays, it uses gamma rays. Gamma rays are a form of ionizing radiation, which means they have enough energy to knock electrons out of atoms. This makes them incredibly powerful, able to penetrate materials that X-rays cannot. Gamma radiography is particularly useful for inspecting dense materials and large objects. It's also more portable than X-ray radiography, making it a good choice for fieldwork. However, it does come with higher safety considerations due to the use of radioactive isotopes. These are just two of the many methods of radiographic testing. each with its own unique features and advantages. X-ray radiography is great for detailed images and a wide range of materials, while gamma radiography excels at penetrating dense materials and is more suitable for fieldwork. When choosing a method, it's important to consider the specific requirements of the test object. What are you trying to find? How dense is the material? How large is the object? These are all factors that can influence which method is most suitable. As we can see, the choice of method depends on the specific requirements of the test object and the information needed. Radiographic testing is more than just a tool, it's a game changer in many industries. But what are the key points to remember? At the heart of our discussion is the understanding that radiographic testing is an indispensable component of non-destructive testing. Its role in maintaining the integrity of structures and materials cannot be understated. It allows us to peer into the inner workings of an object without causing any damage, ensuring safety and quality control. We delved into the step-by-step process of radiographic testing, from the initial preparation to the final interpretation. We saw how meticulous planning and execution are vital to ensure a successful testing process. The importance of a controlled environment was underscored, as even a minute variation can significantly affect the results. We also explored the different methods available for radiographic testing. Each method, be it X-ray or gamma ray, has its unique benefits. X-ray testing, for example, offers the advantage of being easily controllable and is especially suited for testing thicker materials. Gamma rays, on the other hand, have higher penetration power and can be used in conditions where X-rays may not be as effective. But beyond these methods, it's crucial to remember that the effectiveness of radiographic testing ultimately depends on a number of factors. These include the nature of the material being tested, the type of defect being sought, the safety measures in place, and the skill and experience of the operator. Radiographic testing is not just about finding faults, it's about understanding the nature of materials, their strengths and their weaknesses. It's about ensuring that our infrastructures are safe and reliable. So the next time you think about quality control and safety, remember the role radiographic testing plays. After all, it's what's inside that counts.